It's time for the next class. Our next speaker is going to be Zhuang.
Yes.
So whenever you're ready.
Okay. Thank you for having me. This is not my first time to attend the last conference, but first time to present, and my heart is screaming and so nervous about that. Because this is also my rehearsal for the thesis defense in the next week. So hopefully I will, I will give some positive feedback and again more confidence in the defense. Okay, let's start. So this is a part of today's talk will focus on part of the project try to characterization the unilinear residual lattice. I will introduce the definition later. This is a joint work with my thesis advisor Nick Gatos, and I really appreciate his guidance and also appreciate the support by the last conference and our department of University of Denver. So we want to start with the brief introduction of the residual lattice. It's an algebra having lattice reduct, having a monoid reduct, and satisfy the residuation condition, the third item. So a lot of research has been done for the linear ones, the residuated chains. So in 2017, my memory is correct, Nick Gatos and Peter Gibson output a list of all the residuated lattice of size less than or equal to 6. So by then, Nick told me let's have some ambition, saying try to classify all of them, or most of them. So we take the first step by saying let's check the lattice, residuated lattice, with the lattice reduct as an anti-chain in the middle part, but with the top and bottom to make it the lattice. So this is our starting point, and this is also the starting point for my talk today. Actually, we call this residuated lattice over M sub x. We tell the middle part we call the set x. So if we start with the set and at the top and bottom, so that will be the universe for our residuated lattice. And this is the lattice reduct of that. It has a good property saying if two elements in the middle part is distinct, then they are joined and they are incomparable, and the result of the incomparability is that the join is top and the mid is the bottom. So this is the lattice characterization of this kind of residuated lattice. So we know some already known result. I think it's like a kind of exercise problem after some textbook. So if we have a residuated lattice based on M sub x if we say the middle part is closed under multiplication, meanwhile the top and bottom are like zeros for the top part, then we know the middle part x is a cancellator monoid. So this is a well-known result. And from there, today I'm going to characterize not just those x closed under multiplication, but meanwhile it could be unclosed under multiplication. So before we do that, we have to introduce a definition about the zero cancellative monoid. If we say a monoid is zero cancellative, of course it needs a zero as a constant, and if the product will not involve zero, it satisfies the cancellativity. So with this in our mind, and inspired by the fact that residuated lattice is the multiplication distributed over joins, and in our special case, the join of two distinct elements in the middle will always give it the top. So it motivates us to think about what is the product between elements, especially those in the middle and the top. By that, by the different forms, we define two nuisance. One is called U. You can see here, U having the elements in the middle part that plays the role of the left unit for the top. This is why it is called U. And another set is called Z. It plays the role of the left zero for the top element. And it turns out that in a general residuated lattice over M sub x, I will just use M sub x in the following. So in a general M sub x, first, our top element is central. Well, you might have some problem with the integral ones, but I will talk about it later. So here, our M sub x is just having 1 in the middle part, but not the top. So in this case, the top element is central, and the whole universe is the disjoint union of U, Z, and the top and bottom. And if we join the extra element T into the set U, it turns out it's a T-cancellative submonoid of R. And if we join the bottom element in the set Z, also it's closed under multiplication. And the best part is that there are not many kinds of the set Z. The size of it is at most 3. Actually, we exhaust all the possible multiplication tables. There are 4. So now we expose all the possible multiplication tables for Z. I'm going to talk about the integral ones. So we know in the integral case, 1 plays the role at the top. And by the 4 multiplication tables, what we can tell actually is that first one corresponding to the 2-element Boolean algebra, the integral restricted lattice over just the 2-element chain. Second one corresponding to the 3-element hiding algebra, and the third one corresponding to the 3-element and the algebra, and the fourth one corresponding to the 4-element Boolean algebra. With the 4 different types of multiplication tables, we already covered the information about the integral restricted lattice over M sub x. Actually, I have that, just the finite name. So, and the last part about the property of such restricted lattice is that the element in U not just play the role of the multiplicative unit for T, it also play the same role for the elements in Z. So their product will be always B. B is actual element in the set Z. So this is the properties we found, and based on the properties and the information I just mentioned about the integral ones, first I'm going to give a construction and then give the characterization. So now we start with a monoid with a 0T, and it is T-cancellative, another semigroup with 0 bottom, and whose multiplication table is one of the 4 multiplication tables, and we define the universe of the restricted lattice we want is the union, and say now that we want to say it is a form M sub x, so we set our x to be everything except the top and bottom. And then we define a natural ordering to set elements in the x to be pairwise incomparable with each other, and set the top as the top, bottom as the top, bottom as the bottom, and make every element in A to be the unit for elements in B. So we denote by RA, B such resulting algebra. It turns out that this algebra is exactly restricted lattice based on M sub x. And are those all? Yes.
Can you just go back so I can see the multiplication again?
Yes.
No, in your construction.
Yeah. Okay.
Oh yeah. Okay. Thank you.
Yeah. So the constructed R A, B, it is a restricted lattice, and the lattice product is just we described as for x. And it turns out that there's most of them plus the integral ones, the 2-element Boolean, 3-element hiding, 3-element empty algebra, and 4-element Boolean algebra. Those are all the restricted lattice over M sub x. We know the last 3-element restricted lattice is the 3-element order Zhuang chain. We didn't mention it here because it's included in our construction. Just to make sure our set B is trivial, only contain the bottom, and our set A is only the top and 1. That would be sufficient to construct the 3-element Zhuang chain. So by this way, we give the characterization of all the restricted lattice on M sub x. So the next question is, how can we axiomize them? Yes, we can. And our axiomatization just focus on the lattice property. And what we have just see is that the 2 elements in the M sub n are distinct. I mean, the 2 elements in the middle part, then their unit, then their join is the top, and the meet is the bottom. So now here, we not just want to say for m sub x, because that's a very, very small class. We want to talk about more. Okay, we say if two elements are incomparable with each other, then we hope to still get the property that their meet is the bottom and their join is the top. And we use this positive sentence to we didn't choose to use the bounds like this is the general diagram for that. But I want to mention that we didn't choose to add the bounds into our language. We still hope to use the most common language for residual lattice, which means only contain a constant 1, but not extra 2 constants top and bottom. So the first of two variables u1 and u2, they are to cover all the linear cases. Because our main work, our focus is in the nonlinear algebras in the classes. But still, we want to make the axiomatization to be complete. So hope to cover all the linear ones, but we do nothing about the linear ones. The study for the linear residual lattice is very abundant. And if we replace the u1, u2 by t, and by the top and bottom, let's say two elements is the if two elements are incomparable, then the join is the top and the meet is the bottom. And the second axiom, we just use 2, is to describe the height of the lattice. We give a general sentence for a lattice of height less than or equal to n. Use this disjunction of n many equations. Let's say if we have an n plus many chain inside of this lattice, then at least 2 of them will be identical. So this is our idea to describe to axiomatize the case, the property that the lattice is of height at most n. We just take h3 here, because in our case for n sub x, the height is at most 3. And with those two positive sentences, we can say the classes can use the notation URL C3. In the following, I will call linear residual lattice by URL, and the URL3 represents the class of residual lattice whose height is not 3. This is our axiomatization. And Nick in 2004 published a paper, and I think it's named by the equation basis of the joint varieties. In there, he proposed a method that can transfer any universal positive sentence to an infinite set of equations, which is very beneficial in our case that it provides us the equational basis for our classes. So the technique is that we know a positive universal sentence is the disjunction of conjunctions. And for each disjunctive part, we just disjunction of conjunctions of equations. We just talk about those equations and separate it, transfer it to be an equation of the form 1 equals s under t. Sorry, I didn't put here. But you can compare the disjunctive part and the equational part. The positive sentence part and the equational part. The cost we pay is that we put every disjunctive part inside the iterated conjugate. Here, my gamma 1 to gamma 6 belong to the iterated conjunction, and my set x is the set of the variable. Iterated conjunction, it is the composition of finitely many left and right conjunctions with a variable comes from the algebra. So you can take arbitrary iterated conjunctions and put them together. It provides two types of you can substitute any iterated conjunction here into any gamma 1 to gamma 6, and it will provide one of the equations we need to axiomatize this class. It turns out we need infinite many. We try to make it finite, but until now the attempt is didn't get any success or hope for success. I think maybe that's because of my ability that's beyond my ability. So for the axiom URL, we provided those two bunch of infinite equations to axiomize that. Similarly, we can do the this thing for the height 3, h3. We also use the equation at the bottom to give the equational basis for that. So why do we want to give the equational basis? Because we want to talk about the variety generated by the class URL3. So with the equational basis, we know the varieties generated by URL3 are just the models of the axiom for related lattice and the equations corresponding to URL and H3. So we get a variety. The next step should be talk about the generated items, which is the subdirected irreducible algebras inside the variety. But here, instead of the subdirected irreducible ones, we talk about the finitely subirreducible algebras. Because again, in the same paper by Nick, the finitely subdirected irreducible algebra in a variety of restricted lattice has a good property. It says if L is such algebra, it satisfies the equational basis produced just now, the infinite linear equation basis, if only if it satisfies the original positive universal synthesis. So what does this mean in our class? It means that all the finitely subdirectly irreducible residue in the variety is exactly the unilinear ones. Actually, this idea comes from the subdirectly irreducible ones in the semi-linear restricted lattice. The subdirectly irreducible ones are not always linear in that variety, but the finitely subdirectly irreducible ones in that variety is always linear. Because why we call our main target is called union linear, because it's the union of a bunch of disjoint linears. So it will have a lot of similarities between this, our variety and the semi-linear variety of the semi-linear restricted lattice. And this is where the idea comes from. Our focus is on the finitely subdirected ones. Okay, now I think we could agree that the class of the finitely subdirected irreducible ones in the variety, which we denote as SRL, it is the class of URLs. It's not just about the class of URL3. If you add an extra axiom, like the second part of the theorem, we can say all the finitely subdirected irreducible ones in the variety generated by URL3 is URLs. Sorry, it's a little bit redundant, but I want to convince you that our focus on the FSI for the finitely subdirected ones, this is exactly class. Okay. The next is that, yes, another good part about the restricted lattice of MC3 is that generally, if you have more than 3 elements in the middle, then the lattice reductive is simple. And if your middle part consists of just less than or equal to 2 elements, the restricted lattice is simple. So all the finitely generated, all the finitely subdirected irreducible ones are exactly the subdirected irreducible ones in the variety, which are just the restricted lattice of what M squared X. Okay, this is a little bit content about the variety. We named it IM, which is generated by the class URL3. Now we are going to talk about the subvariety of this M. Our main conclusion is that there are uncountably many subvarieties. But we didn't, to prove that, we didn't prove the whole variety generated by URL3, but instead, we just take out the class whose elements are of the form M sub G, and G is a abelian group. So your middle part, your elements in the middle forms a group itself. It's closed down the multiplication, top and bottom are the zero elements or the group elements. We think about the variety generated by that class. It turns out even for that class, even for that variety, the sub-varieties of it is uncountable. And this is our main conclusion, but it turns out that the proof is too low, and when I practice, I feel like maybe it's not, because of the limit of the time, it's not proper for me to even put the sketch of the proof. So I'm just going to go through. Here says the sub-variety lattice of this variety is isomorphic to lattice of strange Z. We have Z, we have P here. I'm going to explain what does this notation mean. What is this lattice? So this lattice P comes from series construction. What we start with is direct power of countably many copies of the chain. And in the entry omega, we take a subset of it. Actually, it's a lattice, elements in the set I. It is a decreasing sequence that are eventually zero. So the examples here are 4211000, 321111000. It looks like a finite sequence, but it's decreasing, but it's an infinite sequence, but we can take the convenience of notation to use that. And this is the elements in the set I, which is a subset of the direct power of countably many copies of the chains. And then we just get another direct power of i's. And again, take a subset, which is eventually zero sequence. So here, if we check the sequence here, actually this is sequence of sequence. We use semicolon to separate the finite sequences, and we use the comma to separate the elements in the finite sequences. So this is an example in the set I to the plus omega. This is why sometimes we call that this is the direct sum of the set i's. So, and what is our P is that we get the direct product between this direct sum of i's and the two element lattice. This is our target, our constructed lattice. And then what are the other parts means, like this O, this Z. We have to define other notations about the we call the Z closed down sets inside the lattice P. So how to define the Z closed down set? Before we import that ideas, we have to say for element in the lattice P, we use this expo of A to denote the maximum number appearing in A. So for example, if we have such sequence, the sequence of finite sequences are just eventually zero sequence, the maximum number here appear is 3, and for this sequence, the maximum number appear here is 4, and we use those 3 and 4 to be the meaning of expo of A. And also we denote the A to be, we know it is a sequence of finite sequences. For each finite sequence, we name it A0, A1, A2. We have to define it to be A0 is just between 0 and 1, which is because it's in the first coordinate, and the AN is in the set I we define above. And we give another notation, prime of A is just a notate. We just collect the index of the finite sequences which are not zero sequences. We collect those indexes. And this is the notation for the elements. For the set, expo of a subset T is just the collection of those maximum number, and the prime of the subset T is the union of those prime sets. So with this notation, I think we are ready to give the definition of Z closed down sets of the lattice P. So we say a down set of P is a Z closed if the expo, for all such element A, the intersection of this down set and the upset of A, one of the expo or prime is unbounded. that happens, then we have to include the join of A and the Zhuang sequence, include them in the Z, in the D. So I think until now it is a very confusing definition, and we must be curious why we want to define such a complex notation. Let me introduce the idea here and give an example, and then tell you the motivation. So an example is that if we have such A, which is 0, 1, 0, 0 inside the P, and if we find out this sequence, which just changed the third coordinate or the third sequence to ask the maximum number to increase, or if we just raise the first coordinate of the second finite sequence, then if either case happens, we have to include this A join the Zhuang sequence inside D. So our D has to include this A join the Zhuang sequence because the XO part is unbounded. Another example is that if we have the index, the prime set of this set D, it is unbounded. So there are always, remember the prime of D join the D intersect the opposite of A, just notate which finite sequence are not zero. If such index keep increasing, then we also have to include this A join the Zhuang sequence. But if we say, okay, I have a finite sequence, let's say the third sequence, I will increase its size. So increase the non-zero number in the third sequence. That happens, we will do nothing. We don't require this condition to be satisfied. And we denote the lattice of such Z-closed downset use this old notation. And let me give you the motivation. Why do we want to introduce such Z-closed downset and such lattice P? Because in our proof, we found out that to show the subvariety of the variety CMG, it's very close. It's close to the representation of the finitely generated abelian groups. And if you know the fundamental theorem of the finitely generated abelian groups, that's of the form every finitely generated abelian group equal to the form we have m many copy Z, and then the rest part of the finite part is a direct product of the P groups. So with that notation, we hope to say, okay, in our proof, we found at some step one of the isomorphism. We see it's better for us to construct such lattice, which is isomorphism to the lattice of all the finitely generated abelian groups, whose ordering is defined by the subgroups. In this way, then people may don't know about the group theory, then they can understand how's the lattice of the subvariety of CMG. I think this is our motivation, and why in the result we just present the lattice of this strange lattice of this Z-closed downset of P. I hope I already make it clear for the motivation for introducing such P and its Z-closed downsets. Okay, we have some corollary here. Remember, we say in this section talking about the subvarieties of this variety M, we have like uncountable many subvarieties. Actually, we don't need to even take the CMG, the variety generated by that class. Even the class M sub ZP, the middle part is the form group ZP. It already will give us the uncountable many subvarieties, because M sub ZP in the downset of the lattice we just mentioned, all the downsets inside it to be the sub-downsets is isomorphic to the power set M. So, and of course, it will result the subvarieties of G and M of the size continuum. And if I am allowed to combine the characterization formally, we mentioned that all the m sub x conjugated over m sub x are of the form R, A, comma B, and we have 4 different types of those elements in place a row of 0 for t. Combined with those 4 different types and define a new poset. Because here the P plus F is not a lattice, but a poset. And use the same technique here we just mentioned, define the Z-closed downset of this P plus F. Then we can show the subvariety lattice of this class CMGZ, which is super variety. The previous one is also isomorphic to the lattice of the Z-closed downsets. See that out of the time, right? Yeah. Okay. Thank you for the attention to my talk, and I don't think I organized it well. Too many things behind it because I didn't find any like a direct reference. But thanks for my bad representation. Thanks for the tolerance and attention. Yeah.
I'm curious, have you looked at how many subvarieties there are if you assume commutativity of the monoid operation?
Assume, like you mean the subvarieties of the variety generated by m sub x?
Yes. Because you're not assuming commutativity of multiplication, right?
I think actually in the proof of MG, the variety generated by, well, the middle part is a abelian group. We did assume the commutativity for that. So the answer is still like uncountable. Yeah.
Any other big question? Thank you. Michelle. We have a coffee break. We restart at 3:35.